The Big Bang model is supported by evidence from many different sources. Here are some of the main points that scientists use to support their claims. First, let's look at the cosmic microwave background radiation, or CMBR. This was discovered in 1964 and is probably the most significant evidence we have for the Big Bang, because it's essentially a snapshot of our universe just 400,000 years after the Big Bang. The CMB is all around us and has an almost perfectly uniform temperature of about 2.7 Kelvin, or 2.7 degrees Celsius. In other words, no matter where you go in the universe, it's pretty much the same temperature. This makes sense if the entire universe started out hot and dense and then expanded. If it didn't expand, then there would be a temperature gradient with the highest temperatures at the center and the lowest temperatures at the edges. But we don't observe this. We observe that no matter where we go, it's the same temperature. You may also be wondering how we can see anything if everything is opaque. Well, the universe wasn't always full of stars and planets and galaxies. It used to be a sea of particles. After the Big Bang, the universe went through a period called the photon epoch, which lasted until about 380,000 years after the Big Bang. During this time, dense plasma in which photons would constantly scatter off of electrons and never get very far. But as the universe expanded, things began to cool. And when things cooled below about 3,000 Kelvin, electrons combined with protons to form neutral hydrogen. This allowed photons to finally travel through space relatively unimpeded, so we're able to see back to this time. Anything that happened before that is invisible to us, because light just couldn't travel through the universe during those first 380,000 years. So looking at the CMB is like looking through a window into the past and seeing what the universe looked. It's like just 380,000 years after the Big Bang. This image here is from the Planck satellite. It's one of the best images we have of the CMB. What you're looking at is not the actual image of the sky. Instead, this shows the temperature variations across the entire sky. The warmer regions indicate areas of space that are slightly hotter than average, while the cooler regions are slightly colder than average. However, even though these temperature variations are tiny, they tell us a lot about what the universe was like in the past. For example, because the universe is expanding, space on the larger scales is being stretched. And if you look closely at the CMB, you can actually see this stretching in action. Scientists call this the Doppler effect. Because the universe is expanding, the light from distant parts of the universe gets stretched, shifting it towards the red end of the spectrum. And this tells us that those parts of the universe are moving away from us. So we know that the universe must have started out smaller than it is now. But perhaps even more important is the fact that the CMB is so smooth. You zoom in on any part of the sky, you won't find any large features. That's because on large enough scales, the universe really is incredibly smooth. In fact, it's so smooth that no matter where you go, you can't tell if you're at the center or at the edge. This is because the universe is the same in every direction. And since it's also the same in every direction, you can't tell if you're at the center or at the edge. This is known as homogeneity. And along with the idea that the universe is the same on large scales is another idea known as isotropy. The idea is that no matter where you go, the laws of physics are the same. Gravity will be the same no matter where you go. The strength of magnetic fields will be the same everywhere, and so on. Homogeneity and isotropy are two of the assumptions of the Big Bang model. They're not part of the model, but rather something that scientists assume the model is true. Then they try to explain how observations fit within this model. In addition to the CMB, we also have other forms of evidence for the Big Bang. For example, we have the abundance of light elements. The Big Bang model predicts that the universe should contain equal amounts of hydrogen, helium, and lithium. And we observe that this is exactly the case. In addition to this, we also have the abundance of heavy elements. The Big Bang doesn't predict the abundance of heavy elements such as iron and uranium because these elements are uncreated in the Big Bang. Instead, they're created inside of stars and then expelled into space when those stars die. So the abundance of heavy elements tells us something about how stars have evolved over time. This is why astronomers study things called stellar nucleosynthesis, which is the study of how elements are made inside of stars. And one final piece of evidence we have for the Big Bang is the abundance of helium-4. You see, the Big Bang model predicts that there should be a lot of helium-3, but not a lot of helium-4. Helium-3 is created during the Big Bang, but helium-4 is created later in the universe, when to helium. 3 nuclei combine to form helium-4 and release a neutron. But this process is unexpected to occur very often in the early universe, because the universe is so spread out. In reality, however, we observe that there is a lot of helium-4 and only small amounts of helium-3. This makes sense if the universe started out hot and dense and then expanded, because if the universe was more spread out, then these nuclei would be less likely to collide and form helium-4. So those are just a few of the pieces of evidence that we have that the Big Bang model is correct. Of course, there are many other pieces of evidence that we haven't covered here. But the main takeaway point is that we don't just have one piece of evidence, but instead have multiple lines of evidence that all converge to the same conclusion. Okay, so now that we've established that the Big Bang model is correct, let's start applying it to real life. We'll do this by stepping through a brief history of the universe. Let's start at the beginning. At t equals 0 seconds, the Big Bang occurs, and the universe begins as an infinitely hot and dense singularity. Then the universe rapidly expands and cools. 1 second after the Big Bang, the universe has expanded by a factor of 1 trillion. Now it's cool enough for protons and neutrons to start forming. For minutes after the Big Bang, most of the protons and neutrons have formed into atomic nuclei. Now the universe is filled with a buzzing, hot plasma of subatomic particles. 380,000 years after the Big Bang, things have really cooled down. Photons are now free to roam the universe. The universe is still unimaginably hot, but it's finally transparent. This allows light to travel freely for the first time. The first stars begin to form 100 million years after the Big Bang. Giant balls of gas begin to collapse under their own gravity. These are the first stars, the population 3 stars. As these stars collapse, they heat up hydrogen gas to millions of degrees, allowing nuclear fusion to begin. The star is born. 1 billion years after the Big Bang, stars begin to gather together into the first galaxies. Some of these stars will eventually become part of the Milky Way. The first planetary systems are born. 4 billion years after the Big Bang, our solar system is one of the first of its kind. A star forms surrounded by a disk of dust and gas. Planetesimals form and then collide and stick together. Eventually Earth forms. 10 billion years after the Big Bang, the universe is unrecognizable from what it was just 10 billion years ago. Stars have begun to die and explode, leaving behind heavy elements that will form new stars and planets. Galaxies have collided and merged to form what we see today. Here we are, watching the universe evolve. So what happens next? Watch this video to find out. Thanks for watching.